Hello, everyone, and welcome to Worksheet 11, Question 2. This is the big one. This is the one where we go over Dijkstra's in a lot of detail. This is the video that I recommend you keep coming back to if you just want mechanical help with doing Dijkstra's. I will make a follow-up video about some of the theoretical implications of Dijkstra's, but the reality is you're probably just confused on the algorithm because it's the biggest, most complicated algorithm we do in this class, and you're looking for a simple walkthrough to go through it. That's what we're going to do. Okay, so here's the agenda for this video, basically. One, we are going to just do Dijkstra's. Then we're going to do an optimized Dijkstra's. Then we are going to do A star, which is just Dijkstra's with a different optimization, or well, two optimizations, I suppose. Okay, so if you look at the worksheet tells you to follow some pseudocode. The pseudocode version they give you is this version. It's the unoptimized kind of basic bare bones bargain bin version of Dijkstra's. It's a good way to start, but it's not very applicable in real life. So after we do that, I'm going to do the algorithm again, but I'm going to put a little optimization in. This is the way that you'll normally see Dijkstra's implemented. And we'll talk about that when we get there. And then we'll talk about A star, which is basically just Dijkstra's with this optimization put in, and then another optimization put in. And we'll do all that. Okay. First things first, let's set up the pieces that we need for Dijkstra's. Okay, so in the basic case, we basically need to have a priority queue for Dijkstra's. This is our fringe, just as if we were doing DFS or BFS, because Dijkstra's is really just a modified form of BFS. We are going to have a dist2 array, and we're going to have an edge2 array. Okay, so now I'm going to basically just write out all of the nodes that we have here. So A, B, C, D, E, F, and G. Okay, so keep in mind that edge2 and dist2 are actually arrays or maps, depending on how you want to implement them. But I'm just gonna kind of pseudocode here. I'm gonna say, if I say dist2 is 6, that means that maybe there's an array and the index we're holding A and has 6, or maybe it's a map and the key is A and the value is 6, right? I'm just doing a little on paper optimization to make things easier, so I don't have to write out a giant array. And we're also going to have a fringe. So the fringe is going to have the same stuff. Like this. It's going to have a value A, B, C, D, E, F, and G in it. Okay, and how we're going to set up the algorithm is we're going to start by putting every single node into the fringe with a priority of infinity aside from the starting node. We're going to start at A, by the way. So A is going to have a priority 0. Every other starting node, or every other node, is going to have an initial priority of infinity. And same thing with dist2. The distance of every node in our array is going to start out as infinity. In other words, before we have started the algorithm, we do not know what the shortest path is from one node to any other node. So we're just going to assume it's infinite. And then as we find shorter paths, we're going to update it with our better and better guesses. Edge2 is basically going to start out as basically null. This is going to track the edges that we take to get to a given path. Okay, here's the setup. And one more time before we start the actual algorithm, we have a fringe. The fringe contains every node in the graph. Our starter node is going to have a priority of 0 because we want it to be the first node that we pop off, and every other node is going to have a priority of infinity, right? Just infinitely high, and we'll update things as we go along. Okay, we have this dist2 array. This dist2 array is the main thing that we're looking for. This dist2 array is what is actually going to tell us the distance from one node to another. So for example, dist2 of E at the end of this algorithm is going to be 5, because we see just by looking at the graph visually that 5 is the shortest path from A to E, right? So in other words, when we're done with the algorithm, dist2 is going to contain all of the length of the shortest paths from A to that node. Edge2 is basically the node that you took to get to that given node. So in other words, we can see here pretty quickly, just looking at the picture, that the shortest path from A to B is just going to be 1, right? Because it just goes directly there. You can just look at that yourself and hopefully see yourself that that's the case. So at the end, our edge2 array is going to have A here for B, right? And the reason is because we took A to get to B, basically. This is going to help us build our actual shortest paths tree afterwards. So because sometimes you don't just want to know, hey, is, F this many units away from A? You also want to know, okay, what path do I need to take to get to F from A? And this is going to help us figure that out at the end of the algorithm. Okay. That's all of the basic setup of everything. So now we're going to basically start the algorithm, and we're going to do a process here. The first thing is we are going to pop a node from a PQ. The second thing we are going to do is we are going to update dist2. The third thing is we are going to update edge2. The final thing we're going to do is update the children priorities. Okay, 4-part process. We're going to do this over and over again, and then at the end, we're going to have our shortest path 3. It's going to be great. Okay, so let's start. The first thing we're going to do is we're going to pop off from the PQ, because that is our first step. Okay, so this PQ, keep in mind, is backed by a heap. This is actually implemented by a heap. I'm just writing it basically as an array for the sake of simplicity, but in real life, it's going to be backed with a heap. Anyways, so first thing we're going to do is we're going to pop off our first node, A. This is kind of the trivial case, right? Okay, so now what we need to do is we need to update dist2. Okay, so what is the distance to A from A? Well, it is just 0. Also notice that dist2 is equal to the priority, right? Because A had a priority of 0 and the distance is going to be 0. That'll become clearer as we do further steps in the algorithm. Another thing to note about Dijkstra's, which is important and we'll talk about a little bit in the next video, is that once you pop a node in Dijkstra's, you'll have found the shortest path, right? Once we pop the node A, we have found the shortest path to A. Once we pop the node to C for the first time, we have found the shortest node to C. I'll explain why that is in the next video, but for now, you can just take my word for it. Okay, so you do that, and then we're going to update edge2. For A, we're not really going to update edge2. This is just a little bit of a technicality, just because remember, edge2 represents what node did you take to get to the node that you're currently popping. We didn't really take a node to get to A, so I'm just going to leave this on. Okay, so we're going to skip over that one for the first iteration, and now we're going to update the priority of the children. Okay, so A has 3 children, B, E, and D, right, with edges respectively of 1, 7, and 2 in terms of weight. And we're going to update those edges in our priority queue if they are less than the current value of the edge in the priority queue. Okay, so A has an edge to B of length 1. 1 is less than infinity, so we're going to take this infinity off and we're going to update the priority, right? Another thing we're going to do is we also need to keep track that the node that we took to update the priority is A. This is going to be later for our edge 2, but basically I'm making a note that's we're saying, okay, I'm on edge A, and if I want to get to B from A, it takes 1, right? So that's going to go in our queue. And we're going to do that for all the other nodes. So you see we have a path to D and E. So to get to D from A is going to take 2. To get to E from A is going to take 7, right? So for every node, I've just marked the distance that we're going to take from the node and the node itself that we are taking, right? The node that precedes this node. Okay, so now we've updated the children. Great. That's the end of our first run of the algorithm. Now let's do the second one. Okay, so first thing is pop from the PQ. What is the minimum item of the PQ? Well, it is B, right? Because B has a priority of 1. Okay, so now we're going to update dist2. What are we going to update it to? We're going to update it to 1, right? Because 1 is the shortest path from A to B. How do we know that? Because we popped it from the queue, and the moment we pop something from the queue, we have found the shortest path, and that shortest path is equal to the priority of the thing that is in the queue. Okay, great, great, great. Next, we are going to update edge 2. This is where keeping track of this A comes in handy. Edge 2 is just going to be A. Why? Because in order to get to B via the shortest path, you first take A, right? Okay, and now we're going to update the children. B only has 1 child, it is C. So what is the distance to C? The distance to C is 4. Why is it 4? Because it takes 1 to get to B, and then it takes 3 to get from B to C, right? So we're going to update the priority of C to be 4, and we are going to say, okay, the node that takes us to C via what we think is currently the shortest path is B, right? Keep in mind, these priorities are the total distance from A. So the priority of C is 4, not 3. It's the distance it takes to get to B, right? Plus the distance to get from B to C. Okay, B only has one child, so now we can continue with the algorithm. Okay, so we're going to pop from the PQ again. What's the minimum element of the PQ? It is D, so we're going to pop off D. Okay, so we're going to update dist2, and we're going to update edge2. What is the distance to D? Well, it is just the value of the priority. It is 2. What edge do we take to get to D? Well, we just went directly from A to get to D. Great. Okay, now it's time to update the children. D only has one child, just like C, and that child is E. Okay, so currently, the shortest path we have found to E is traveling via node A, and it's a total distance of 7, right? It's just this path. So now what we're going to say is, okay, is it faster to, instead of going from whatever path we have currently, is it faster to go first to D and then to E? And in this case, it is, right? Because you can see it takes 2 to get to D, and then it takes 3 additionally to go from D to E, right? So we're going to update in our fringe. We're going to say, okay, we found a shorter way to get to E. It's only going to take 5. And we get there no longer via node A, but via node D. So I'm going to update it like this, right? Okay. Next iteration of the loop. We're going to pop the minimum. It's C. Okay, so what is the total distance? Or the dist to C? It's just going to be 4, like that. What node did we take to get to C? We took B, right? The shortest way to get from A to C is via the node B. And then we are going to update its children. Okay, C has 2 children. It has F and it has G. F and G are both infinite right now in our priority queue. So without even comparing, we know that we're going to have to update their values, right? So what is the distance to F via C? The distance to F via C is 6, right? How do you do that? Well, you can just look up what is the minimum distance to C is 4. And then the distance from C to where we want to go next, F is 2. Add those together, you get 6. Okay, great. We do a similar thing with G. We say, okay, what is the distance to G? What is the distance to G? It's equal to the distance to C plus the distance from C to G. The distance to C is 4. The distance from C to G is 4. We add those together, we get 8. 8 is less than infinity. So we're going to say 8. And we're going to say, okay, we get there via C. Great. Okay, we've updated everything. Now you see that all of the elements in our fringe are no longer infinite. We might still change them, but we found a path to every node at this point. Whether or not it's the shortest path is yet to be seen. Okay, great. Let's continue. So now we pop the next node. It is going to be E. What is the length of the path to E? It is going to be 5. What node did we take to get there? Well, we took D to get there, remember, because we found a shorter path to E through D after we found the original path from A, right? Even though it's more nodes along the way, it's a shorter path overall. And then we are going to update its children. Okay, so E has one child, it is G. How long would it take to get to G via E? Well, it takes 5 to get to E, and then it takes 4 to get from E to G, meaning it would take a total of 9 to get to G via E. So we look here, but then we see, oh, G, we've already found a path of length 8, right? We've already found a shorter path, so we're not going to update this value because we don't want to update it with a longer path. So we're not going to do anything basically to the fringe. We're not going to change any children. Okay, continuing along. Great. F is going to be total distance of 6. And we are going to get there via C. So we're just going to update that. Now we're going to update the children. Okay, so we see that the total distance to F is 6. And then the distance from F to G is 1, meaning that we can go to G via F with a total distance of 7. That is better than the current total distance of 8 that we have found. So we're going to update the queue. We're going to say, okay, if we take node F, we can get there in 7. And then we move on to our last iteration of the algorithm. We're going to pop this thing off, G. I'm going to say, how long does it take to get to G? It takes 7. From what node do you come? You come from F. And now we are all done. Okay, so this is now the kind of end result of our algorithm. We see that we have 0, 1, 4, 2, 5, 6, and 7 are the distances of the shortest paths, and we can also reconstruct the shortest path trees here. So let's say now that I've run this algorithm and I want to say, okay, how do I get to F, right? I know that F is 6 units away from A, but how do I get there? Well, here's what you do. You go to F and you see, okay, I got to F via C. So you know you can build it backwards, basically. You know that you came to F via C. Then you can go to C and you can see, okay, well, we got to C via B, and you can build it backwards. Then you can go to B and say, okay, we got to B via A. You go to A and you see, okay, A was the start. Therefore, you just take that path, F, C, B, A, you flip it around to A, B, C, F, and that is the shortest path to F, right? This is very, very similar. If you remember weighted quick unions, this is very, very similar to how we were able to determine the face of a set or the head of a set in a quick union. We were able to just basically trace up the parents through an array and build it backwards. We're doing the same thing here. So that's why you have this edge 2 array. You don't strictly need it to run the algorithm, but if you want to construct the shortest path tree afterwards, you do, if you want more than just the actual distances. Okay, cool, cool, cool. That is the first one done. That's basic Dijkstra's. Now let's do a quick optimization to Dijkstra's. I'm gonna rerun the algorithm. I'm gonna do it a little bit faster. But we're gonna do a quick optimization. So the main thing we're going to do is we're going to change how the fringe works. Okay, so the first thing we did in our regular Dijkstra's algorithm is we put every single node in the graph into the fringe. However, this is not practical for a lot of applications, right? The classic example that you would use Dijkstra's in is, for example, a map. So imagine you had a map of like the United States, and each node represented a street corner or something, and every distance represented the length of a road. And you want to find the shortest road, the shortest path from one place to another. Okay, well, the problem with that is there are millions and millions of street corners in the United States, meaning there would be millions and millions of nodes in a graph that represent the United States. And if you just try to put 1 million nodes into your priority queue, that sounds like a great way for your computer to run out of memory. In other words, this does not scale up well because it scales memory-wise linearly with the number of nodes that you want to search. However, we don't need all of the nodes at once, right? We only need the nodes that we're looking at next, right? If you remember when I put everything in the queue, there were a bunch of nodes in there originally that were just sitting at infinity, and we didn't even use them for a long time. We didn't even use them until we popped other nodes, right? So what we're going to do is our optimization is, instead of adding everything to the priority queue initially, we are going to only add children as we see them for the first time. And that is going to make sure that we don't have a ton of extra elements in a priority queue. Okay, another thing that's important is this is going to necessitate having a scene set. So I'm going to have a set of scene vertices before. In other words, once we pop a vertex, we're going to put in the scene set. So let's change our algorithm a little bit here. So we are now going to pop from the priority queue, and we are going to also add to scene. And then instead of updating the children priority, you're going to add the children priority. Okay, so I'm going to reorder our priority queue. I'm going to draw it a little differently too. So the priority queue is going to have a node, it's going to have a priority, and it's going to have an edge 2, right? Remember how in the past, with the first run of the algorithm, I had every node, it had a given priority, and then in parentheses, it had the node that took us there. This is going to be the same criteria here. I'm just drawing it a little differently, and you'll probably see why in a minute. Okay. First thing we're going to do is we're going to add our starting node, which again is A. Our starting node is A, that's priority of 0, and the edge we took to get there is null. It doesn't really matter in this case. Okay, this is our setup for our run 2 of Dijkstra's. This one I think is easier personally, but you can do it whatever way is most comfortable for you. This is the way it's actually going to be implemented in more kind of modern data structures. Okay, so the first thing we're going to do is we're going to pop A off of our fringe, and we're going to add it to the scene set. We've seen A, great. Oh, also, we're going to add the children as long as they're unseen. That's the algorithm. Anyway, so we're going to add A to our scene set. Okay, great. Now we are going to update our dist2. The distance from A to A is of course 0. Update edge 2. Again, it's kind of trivial in the first run of the algorithm. We don't really take an edge to get to A. Now we're going to add the children. Okay. Keep in mind the children are not in the fringe already, so we're going to add them into the fringe rather than updating things that are already there. So what do we need to add? We need to add B, we need to add E, and we need to add D, and we need to add them all based off the priorities. So the priority of B is going to be 1. The edge we took to get there is A. The priority of D is going to be 2. The edge we took to get there is A. Also, the priority of E is going to be 7. The edge we took to get there is A. Right. I've personally gone ahead and sorted them myself. Keep in mind, of course, the priority queue data structure is going to internally sort these things. So this is basically what we have. We've got the children, and now we're going to continue with our next loop of the algorithm. Okay, so we are going to pop and add scene. Okay, so we're going to pop B because it's the minimum element. We're going to say the distance to B is 1 because, again, once we pop something, we found the minimum distance. We are going to add it to our scene set. We're going to say the edge we took to get to B was A, right? And now we're going to add its children. It has 1 child, it is C. What is the distance to C? The total distance is 4. So it's going to end up going like right here, basically in our priority queue. And we got there via edge B. Great. Pop the next thing. That's D. Okay. So we're going to pop D. We're going to add it to our scene set. We are going to update its dist 2 to be 2. We're going to update its edge 2 to be A, just as before. Now we're going to pop the next thing. The next thing is C. So we're going to pop that right there. We're going to say, okay, the distance to C is going to be 4. We're going to add it to our scene set. The edge we took to get to C is B. Now we're going to add its unseen children. Okay, so its unseen children are just going to be I fucked this up. Damn it. Okay, so now we're ready to start this algorithm. One more note I'm going to add here is we're only going to add the unseen children. I forgot to write earlier. Okay, anyways, so let's start the algorithm. First things first, we pop off A, just as before. We update the distance to A. It's going to be 0. We add it to our scene set. Great. We update the edge to. It's going to be null in this case because it's the first one we're doing. Okay, so now we're going to add the children of A. There are 3 children of A, B, D, and E. So we're going to end up with B, D, and E in here with distance 7, 2, and 1 respectively, because that's the distance they take from A. And they all come from A, right? So I'm going to say, okay, the edge 2 to get to any of them is from A. Great, so we've added all the children. I've sorted them myself, but of course the internal priority queue data structure is going to sort them for you, so you don't really have to worry about that. Okay, so now we can run the next loop of our algorithm. So now we're going to pop off B, which is distance 1. Remember that the second we pop off a node, that distance we find is the minimum distance possible. We're going to say, what edge do we take to get to B? We took A. We're going to add it to our scene set. Okay, great. Run the next loop of the algorithm. Oh, wait, sorry. I have to add the children first. We have to add the children of B. B has 1 child. It is C. So it's going to end up going right here with a total distance of 4 away. And it is going to take the node B to get there. Okay. Now that we've added the children, we can pop the next one. The next one is D. Okay, so we are going to pop D. The minimum distance to D is 2. The edge we took to get to D is A. We're going to add it to our scene set. And now we're going to add the children of D. D has 1 child. It is E. What is the priority of E that we want to add? It is 5 because it takes 2 to get to D, and then it takes 3 to get from D to E. So we're going to add it to our priority queue. Now what you'll notice is that there's already an E in our priority queue, but we're just going to add another one anyways. So we're going to add another E. It's going to go right here in between these two. And notice it has a different priority and it has a different node to get there, right? In other words, what we're saying is, hey, we have this path. We can get to E via A that takes 7, or we can get to E via B. It takes 5, right? And it's actually okay to have both of these in the priority queue at the same time, because if you think of it, the priority queue is always going to pop off the minimum element first. In other words, we're never going to pop this element before this element. So we're always still going to pop, we're always still going to maintain this property that the first time we pop something, that is the minimum path. Okay, so let's keep going. Great, so we're going to pop C. Okay, so C is 4, great, and we got to C via B, so we add this, we add it to our scene set. Okay, now we're going to add C's children. It has 2 children, F and G. To get to F is distance 6, to get to G is going to be distance 8. So we're going to add those to the priority queue. I'm going to redraw this a little bit just to make myself more room in the priority queue. So I'm going to move this over here, and then we say, okay. To get to F is 6, we get there via C. To get to G is 8, and we also get there via C. So the priority queue is getting a little squished together just because it's hard to draw the picture, but you can see now, here's what we have. Okay, great. Next thing we're going to do is we're going to pop E. Great, the minimum distance to E is 5. Sure, we're going to add to our scene set. We are then going to update the edge 2. So we got to E via A. Notice that we pop the one that, or sorry, not via A, via B. Notice we pop the one that comes from B, not the one that pops from A. So we're going to add that one. And then we're going to add the children of E. The children of E are G, and it would take 9 to get there. Let me move my fringe over a little bit, just so that I can let's move this over a little bit, just so it's easier to draw. So we're going to add G here with a distance 9 coming via E. Okay, we're going to add that, even though we're not going to pop it, right? Because there's already a G that's sooner on the queue. Okay, next thing we're going to do, pop the next thing, is F. Distance F is 6. We got there via C. We add F to our scene. And then we're going to add as children. F has 1 child. It is G at distance 7. So again, let me make a little room right here. If we go to G via F, we can do it in distance 7. Okay, so the next thing to pop is going to be E. But here's the thing, we have already seen E. So we are not going to, we're going to basically pop it, but we're going to ignore it, right? We're not going to include it in our table because we've already, we've already decided that the shortest path is 5. So it doesn't make sense to update it now that it's 7. So we're basically going to skip over it. That's why we have this nice scene thing over here. Okay, now we're going to pop the next thing, which is just going to be G. That's going to give us a 7. It's going to say the fastest way to get there is via C. And now we're done with the algorithm again. So we've arrived at the same conclusion, but notice that we never had more than, I believe, 5 nodes in our priority queue at one time, as opposed to just always having all 7 of them. And you can imagine this is going to scale up really, really well when you have like a really, really big map full of things, and you don't want to put all of them in at once. Okay. Great. So now we have done the optimized version of Dijkstra's. Check. Now it's time to do A star. Okay, hello. And now we're all set up for A star. So A star is going to be the exact same thing as Dijkstra's, except we're going to add in heuristics. So I'm going to do the original version of Dijkstra's that we did without the optimization, but you could also do it with the optimization. It doesn't really matter. I'm just going back to the version where we add everything into the priority queue at once. So basically, we're going to do everything the exact same way we did before, except now we're going to add in some heuristics. So what are the heuristics? Well, we're trying to get to know G. So these heuristics are just estimated distances from any given node to G. So this means we estimate the distance from A to G is 7. E, we estimate the distance from E to G is 7 or is 3. We don't know if that's true, etc. But that's going to be our estimate, and we're going to use it to help guide our priority queue. The idea here is we are hopefully going to go through the priority queue in a way that is more efficient, right? We're going to visit fewer unnecessary nodes. For example, from the first time we did this, you can probably see that the shortest path from A to G overall is this one. right, is A, B, C, F, G, right? So there's no need to explore E. But in the original Dijkstra's algorithm, we did, just because we didn't really know where we were going. Now we have a bit of a guide that will help us along. Okay, first thing we're going to do is we're going to add A into the fringe. Before, we added A into the fringe just with the value of 0. But now we're going to add A into the fringe with first the distance from its parent node to itself, which is just 0, trivially with the first case. And we are also going to add this heuristic to it, which is 7, right? So we're going to actually start with our initial node at priority 7 because we're estimating that it's 7 away, right? Okay, so now we're ready to start the algorithm as before. So first thing we do is we're going to pop off A. We are going to update its dist2. What is its dist2? It is 0. It's not 7. Before, when just regular Dijkstra's, we could say, okay, the distance is just going to be equal to the priority. Now the priority has this extra factor in it. It's not based solely off the distance, so it's not quite that simple. We need to make sure that we are adding the actual distance and not our estimate anymore. But it's still basically the same. We just add that, and now we say the edge we took to get to A is just going to be null because of the trivial first case. Great. Now we're going to add the children, and we're going to add them in with heuristic. So same thing as before, where we're updating B, D, and E, but now we're going to update them with their distances plus the heuristic. Okay, so what is the distance to get to B? The distance to get to B from A is 1. If we add in B's heuristic, which is 6, we get a total of 7. So our estimate is 7. Let's keep track that we came here from node A, just as before. And let's do the same thing with D. A to D is 2. 2 plus 6, which is the heuristic value, is going to be 8. We came there from node A. Great. Now we're going to look at E. E's distance is 7. The heuristic value of E is 3. So 3 plus 7 is going to be 10. And we came there from node A. Great, great, great. Okay, next thing we're going to do is go back to the top and continue our iteration. So we're going to pop off B, which is the next highest priority thing. We're going to update our dist2. Our dist2B is 1, right? Because we need to subtract out the heuristic again when we do the distance 2. And then our edge 2 for B is going to be A, because A is the edge we took to get there. Okay, great. Now we're going to update the children of B. B has 1 child. It is C. Okay, so what is the distance it takes to get to C based off our heuristic? Well, it takes 4 total to get to C from B, right? Because A plus B, then B plus C, and the heuristic for C is 3. So we're going to say 4 plus 3 is equal to 7. Okay. 7, we got there via node B. Important thing here to note is, remember, what we are adding is we are adding, basically, whenever we add a child, we are adding the node, the distance to get to the parent, right, which in this case, A to B is 1, plus the distance to get from the parent to the child, which is B to C, 3, plus the estimated heuristic of the child, which is 3 in this case. Notice that we are not adding B's heuristic and C's heuristic together. We're not double dipping on heuristics. We're only adding one value at once. That would mess things up if we add both of them. So keep in mind, the big thing here is, remember, it's not as simple anymore as just saying, okay, the priority is the distance, or the priority is the factor we're adding by. Be very careful how you add in the heuristics. Okay. But yeah, so we just did that. And now we're going to pop the next thing off the queue. Now remember, the first time we ran Dijkstra's, the next thing we popped off the queue at this point was D, because D was 2 away from A. Now we see that we're actually going to pop off C first, because C now has the lowest priority, right? Because D and E have both been weighted by their heuristics to be bigger. Okay, so we're going to pop off C, which means the distance to C, we're going to calculate as 4, because remember, it's the distance from A to B, then plus B to C. We're going to update our edge 2 to say we got there via B, and now we're going to update our children. Okay, so F. Total distance to get to F is distance from A to C, which is 4, plus C to F, which is 2, plus the heuristic. F's heuristic is 1, so that's a total of 7. So we're going to get priority 7 here coming from node C. And then G is the same thing. We're going to get 8 plus the heuristic. The heuristic, oh, there is no heuristic for G because G is our actual destination node, right? So let's just assume the heuristic is 0 because, of course, the distance from your destination to your destination is 0. So we're just going to say, okay, to get to G is going to take us 8. That's if we come from C. Okay, great. Pop off the next thing. What is the next thing? It is F, right? Because F is the next lowest thing in the priority queue. What is the minimum distance to F? It is 6. It is 6 if we go there from C, so we can update our edge 2. Now we can update the children. So If we want to do that, we say, what is the distance it took to get to F? C, what is the distance from F to G? So it is going to be 6 plus 1 is going to give us 7. What is our heuristic for G? Trivially, it's going to be 0. So now we're going to say, okay, we found a heuristic. We have found that G is 7 away with our estimate, and that is the case. If we go from node F, pop off the next thing from the queue, it's going to be G, right? And we now know that the minimum distance G is 7, and the node we take to get there is F. And we can actually just stop our algorithm right there, right? Because the whole point of this particular run is we didn't want to find the shortest path tree from A to every node. We just wanted to find the shortest path from A to G, right? You can think of it like if this is a mapping application and you're trying to map from one place to another place, you don't really care about the shortest path ever in between. You only care about the shortest path from where you're starting to where you're going. And here we found it without unnecessarily exploring these nodes. And we did it because we were able to use a heuristic to kind of guide our search in one direction. Okay, that's everything. That's 3 ways to approach shortest paths: our original Dijkstra's, our optimized Dijkstra's, and our A-star. Keep in mind the A-star can or cannot have that optimization that we used in part 2 if you want. I hope this was helpful, and I will see you in the next video.